Hello guys, in this lecture I'm gonna do one more example on homogeneous and rotational transformations, and I'm gonna do a brief introductions to DH transformations. So DH transformations is another form of the homogeneous transformation. So DH is actually also another homogeneous transformation, which basically have a rotation matrix on the inside. It has the coordinate of your other point, for example, in frame one, but basically in a more conventional way. So if I do DH1 in frame 0, like, O1 and 0, for example, and then this is R1, 0. But basically, it's actually a function of 4 parameters, basically, A, alpha, D, and then theta. And I'm going to do a very brief introduction on that toward the end of the lecture. And we're going to be using DH transformations for actual manipulators, basically. It's more conventional way. In the time being, we're going to continue with our study on rotational and homogeneous transformations, and we're going to be doing this example. When you are doing your own robot, basically, obviously, you have the freedom to put whatever the frame that you want, right? It doesn't actually have to obey the DH convention. But in in industrial robots, for example, if you want to buy a robot, basically, you will they can provide you these parameters, basically, so you can directly obtain that DH transformation. Okay, let me do this example, this exercise, and what I would like you guys to do, maybe you can also spend some time before I do it, and then try to actually write the homogeneous transformation between frame B to frame A, right? What is HBA, by the way? HBA basically is that homogeneous transformation which I can use to convert. Let's say I have a vector in frame B. If I want to write that vector in frame A, basically I would have to multiply it by HAB, and it's going to give me X in frame A, right? And if I'm doing this whole operation, basically the homogeneous transformation, what will I get, basically? I will literally get, let me actually draw that for you guys here. So if I'm applying this homogeneous transformation, if I have a vector in frame B, right? So this XB right here, basically, right? It means that you basically know the projection of this vector into this frame. It's kind of XB value, YB value, and then ZB value. And then when you multiply it by HAB, because you have the 1 here, right? And because you have the 1 below that XB, basically, you would be finding what the coordinate of this point, right? The tip of that vector in frame A. All right, if you put 0 here, right, or if you put basically, well, we always write our when we program our homogeneous transformation, we always want to put a 1 here, right? If I want to only get the actual rotational transformation, literally, I would like to get what would be the projection of this vector into X, the projection of this smaller vector into Y, A, and then the projection of this vector into Z. Then I would basically X, I would basically put 0 at the bottom, right? And then that 0 will multiply the O, and then it will basically kill the offset. Okay, that is it regarding that. So let us actually do this. So we're trying to find HAB. How can I find HAB? So let's recall what is actually HAB. HAB is you're finding XB in frame A, YB in frame A, and then ZB in frame A. And then ZB in frame A. Okay, so let us find what XB in frame A, YB in frame A, and ZB in frame A. If I actually look into that figure, you will see that basically you have XA like that, you have YA, and then you have ZA, and then basically, XB is perpendicular to that link. Basically, it makes an angle theta, right? So this is your XB making an angle theta with XA. And then this is perpendicular, basically. So this guy has to be what? Has to be theta, right? And then this is your YB. And then ZB is in the same direction. Wait, okay, XB is like that. This guy is ZB here, right? This guy is ZB. And Sorry about that. So YB is actually in opposite direction as ZA. Okay. So we have XA, YA, ZA. We know XB is makes an angle theta with XA, and then ZB makes an angle theta with YA, right? Why? Because your ZB basically is along this direction, and then you have this angle theta. Therefore, this angle has to be theta. Okay, let's quickly do that. So what is XB in frame A? Can someone help me out with that? So XB in frame A, basically, I'm gonna project vector XB on frame on initially XA, and then on YA, and then on ZA. So we know you're gonna basically get cosine theta, right? So the projection of vector XB into XA will be cosine theta. Projection of vector XB into YA is sine theta, and then into our into ZA basically is going to be 0. Why? Because this vector XB is in basically plane XA, YA. Now let's look into YB in frame A. What is YB in frame A? So we know YB, if you look into the presentation, we know YB is in opposite direction of ZA, right? So it's going to be 0, 0, minus 1. Right? Why is it minus 1? Well, YB has no component along XC, neither any component along YA. It is in opposite direction as ZA. So it's going to be minus, right? How about ZB in frame A? How would you write that? So this is your ZB. You know, ZB basically is opposite direction as XA. So it's minus sine theta. How about along YA is going to be cosine theta. And then here it's going to be 0. Right, it has no components. So now I can actually write my homogeneous transformation. Well, let's actually find OB in frame A. What do you think OB in frame A? So it has an X component. So here what I can do is to find the X component at this point, I can do L cosine theta, right? So L cosine theta, it will give me the coordinate of this point along XA, and then I have to subtract minus L sine theta. If this guy is theta, then this guy right there is theta. Right, let me quickly draw that for you. So if this angle is theta, then this angle here has to be theta, right? Okay, so X component is going to be L cosine theta minus L sine theta, right? So L cosine theta minus L sine theta. How about the Y component? It's going to be L sine theta, right? Plus L cosine theta. And then the last one is 0. So I can now very quickly write my HAB, and then I can write, cosine theta, sine theta 0, 0, YB is 0, 0, minus 1, 0, ZB is going to be minus sine theta, cosine theta 0, 0, and then the last one is going to be what? L cosine theta minus L sine theta, and then this whole thing is parenthesis 0 and then 1. Okay, so that is your HAB. Now let's actually do this in Matlab and then validate to get the same result. I encourage you also, guys, to also do these problems on your own to make sure that you are actually able to do this on your own. Okay, so what I'll do is, so this is my Matlab, and then I'm gonna move it. Let me. Okay, so now let me stop this feed. Just a second. Okay, I need to close this. Okay, here you go. So let me stop the video. Come here. Close this to this. Here we go. Okay, so now basically if I would like to do this in Matlab, how can I do this? So I'm gonna actually clear variables. So basically I'm on my command window, I'm cleaning all my variables. Now I would like to actually write that homogeneous transformation. Like I said last time, basically what you want to do is you want to follow the sequence of rotations and translations from your starting frame to the frame about which you are trying to find the mapping, right? So basically here finding H, A to B, right? All right, this is what we're doing right now. So we're finding the homogeneous transformation between frame A and frame B. So if you have a vector in frame B, you simply multiply it by this homogeneous transformation, and then you can get the coordinate of the point, the tip of that vector basically in the base frame or in frame A. So how do we do that? So I think, so what I did is basically in my workspace, I have already defined my rotational matrices. So this is the rotation transformation about X. We described that last time. So now I have all of them, right? So I have rotation about X. I have rotation about Y. I bring it here. So this is my rotation about Y. All these basically are from my slides. And then rotation about Z. Translation about X. Again, all of these guys are 4x4 so that I can multiply them, right? So rotation about X, simply I'm adding this D offset. Make sure that the name that you write here basically is the same name that you save your function. If I actually modify that, you will see basically it will tip an error, right? So it has to be always the same name, okay, as a file that you actually save. Okay, how can I do that? So I'm gonna begin by rotating this transformation and then moving it into this, right? So it has to basically be identical on the other end. So what I'll do is I'm going to begin by rotating about the z-axis by a value of theta, but value is not defined, so I'm going to actually do sims theta, and let me actually do L. So we have the angle theta, and then as L are defined as symbolic variables. So I'm going to start by doing rotation about z, right? So I'm starting from frame A. I'm rotating about z by theta. Now my vector xa is pointing along this length, right? Okay, now I'm gonna do what? I'm gonna translate, right? I'm gonna translate about X by a value of L, right? So now basically I'm here and my XA is pointing toward this direction, and now XA is basically parallel to XB. Now I wanna do what? Now I'm gonna basically translate, right? Translate about what? Okay. So we translate about X by L. Right now, I want to translate. So my Y right now is basically along length 2. Right? So I can now translate by Y by length by a length L. Right. So I translated about X by a length L. Now I'm here. My XA now is parallel to XP because of my initial rotation. Now I want to translate along Y by a distance L. Right. So now my XA, now the two frames basically are collocated. XA is in the same direction as XB, but now I have YA is in the same direction as YB, as ZB, I'm sorry, and then ZA is here. So now I need to rotate, right? I need to rotate by X, by how much? By minus pi over 2. So if I rotate by X, about X by minus pi over 2, basically, I'm going to basically, ZA, which is perpendicular to the paper toward me, is going to be in line with ZB, and then YA is going to be in the same way as YB. So now this is my rotation transformation. Remember I mentioned something about rounding. So when you do cosine of pi over 2, Matlab doesn't give you like exactly like 0. It could give you like, 10 to the minus 15. And when you do this, basically it actually gets incorporated into this rotation transformation. So if you do this, I want to show you that. So you end up with these values, which we don't want, right? So a good thing would be to actually round this guy. Depending on which version of Matlab you use, sometimes the round function will not work. So I created my own rounding function. So I can basically round this array basically, and then here it's parallelized basically that round function. I can basically define how many significant figures I'm gonna do the rounding by. So if I do this basically, I clean that up, and then I'm gonna show you my rounding function, which is what I have basically here. So what is it? Here you go. It's very basic rounding function basically. In my case, basically round would only work on, I can't put two arguments basically. I would put like, round of 2.5, right? It would give me, let's say the number was like 2.561. if I do my round here, basically, I will not be able to specify for how many significant figures I can do, right? Like, you know, this function, if I have pi, basically, if I put 3, basically, I should be able, like, if you should try this, and if that works for you, then you just use the round function. But if that doesn't work for you, it has too many input arguments. So in our case, in my case, basically, I can only, like, you know, round for one significant figure. If you are able to specify how many significant figures you can round it up, then your version is good. If not, then you want to make this function to be able to round the cosine or the sine, or you might actually figure it out on your own, basically how you actually write the homogeneous transformations in the function, basically to basically, you know, if you solve cosine 0, or if the number is very close to 0, then just round it directly. Okay, this is a function here, but okay, back to what we were doing. So this is what we're doing here. So I'm just going to copy this, just clear this command window. I'm going to call HB is equal to what I just wrote. Okay, let's actually compare this guy to what we did in our initial analysis. I want to start the video, right? And you can see basically this is exactly our result, right? So we have cosine theta, sine theta 0, 0, 0, 0, minus 1, 0, minus sine theta, cosine theta 0, 0, and then L cosine theta, minus L sine theta, and L cosine theta 0, 1. Okay, so it all basically matches. Okay, let's continue here. So this is what we did, and then this is what we have. This is basically the same result, right? If you have cosine theta plus pi over 4, basically, what another way of doing that is basically you can simply get the length here, right? So if this is the length here is going to be a square root of L squared plus L squared, which is square root of 2 times L. This is the first component, and then you can take this whole angle. So if this angle here is going to be, let me just annotate this so you can see that, and I want to draw it as a line, right? So what is that angle? What is this angle right there? So this angle is pi over 4, right? So this angle is pi over 4 plus theta. So it's just like that. So this whole angle is pi over 4 plus theta. So this whole, if we want to get the x coordinate of this point, you will simply do square root of 2 times L times cosine of theta plus pi over 4, which is what you see here. Okay, so easy way you do it, basically, if you understand the concept, you will find this to be really simple. Okay. Okay, guys, so this is what the homogeneous transformations are about, and basically this lecture really sums up our work with homogeneous transformations. And you know, I'm going to begin by doing a brief introduction on the DH transformations, and we will be done today. So, okay. All right, so here's the DH transformations, and sometimes if you are working with, you know, articulated robot with so many axes, etc., you might want to work with a conventional method for putting the frames, basically, right? We said every link on the robot will have its own frame, right? But where you actually, let me zoom in on this, where you actually put the frame is up to you, right? Ultimately, your goal is to be able to simply perform you know, transformations between the end effector, or where the robot is, and your base frame. And sometimes, you know, your the end effector basically on the robot will give you a position of an object, and you know, it will give it to you in frame 6 basically. Let's say you have a camera connected on your end effector, you will be able to use H06 to find the coordinate of that point in your base frame, and vice versa. Sometimes you can have a camera like in your world frame, and you want to basically convert what that camera is seeing, or the object that the camera is seeing, into the end effector frame. So you'll know basically how to move along the end effector frame. So if you map, for example, an object and turned out to be along, you know, like X6, for example, you know that all you need to do is just move along X6, and then you will approach it. So there is a way that there's a conventional way for attaching frames into links, right? And we said each link will have its own frame, and the convention is called the DH parameters, or the Donovan-Harterberg parameters for manipulation. And this is what basically is the convention for standard robots, industrial robots, etc. So this is how you place a frame. The most important thing to realize here is that you begin by basically putting your z-axis All right, so Z0 basically is going to be connected to ground, right? But it is the axis of actuation of link 1, all right? So Z0 is the axis of actuation, meaning that if you have a revolute joint, the Z basically is going to be your the axis that is along the motor, right? Along the motor shaft is what is basically creating that rotation. And then you will see it here basically. If the joint is translational, it will be along the translational axis, all right? But if it's rotational, like I said, it's going to be the axis of rotation. That is basically from the gearbox to the motor, basically, right? Pointing in that direction. Okay, so this is a, you know, if you have a positive direction, basically, you use the right-hand rule, basically. Your thumb is going to be your thumb of your right hand, not the left hand. Okay, so you put your thumb along the axis, and then your hand will basically dictate the rotation of direction. Okay, so it will be like this, right? So this is my thumb along, let me put that, so, okay, so this would be my right hand, this is my z-axis, and then this is theta, okay? So this is the direction of, this is how the motor is basically mounted. This is the motor, the gearbox, right? Your z is along that direction, and then this is your rotation direction. Okay, so this is your Z0 basically drives link 1, Z1 basically drives link 2, right? So Z0 would be along the first motor, right? And driving link 1, and then Z2 is along the second motor driving link 2, or Z1 driving link 2, and then Z2 drives link 3, so on and so forth. This is how you put the Z-axis. Now, if you want now to put the X-axis, so the X0 obviously would have to be perpendicular to Z0, and that's it. But the most important thing here, X1 actually has to be perpendicular to both Z1 and Z0. Okay, X1, which you put on link 1, right, on frame 1, it actually has to be perpendicular to both Z1 and Z0. And X2 has to be perpendicular to Z2 and then Z3. So this is very important. Okay? This is the most important thing about the DH parameters, that the X1 that you put on link 1 or frame 1, so you've already established your Z0, right? What it means is you put X0, you're free basically, it's your base, right? But X1 basically has to be perpendicular to both Z1 and Z0. X2 has to be perpendicular to both Z2 and Z1. Once you actually have X1 and then Z0, I'm sorry, X0 and then Z0, then you'll be able to find your Y0 very easily by using the right-hand rule. But we don't actually need the Y0 for your DH transformations. All you need is basically X0 and Z0, or X and then the Z vectors. Because anyway, when you have X and then Z basically as a frame, as an orthogonal plane, then your Y is already located. Then we can say that the DH transformation is actually a function of only 4 variables, right? The first variable is A, which is the distance, the common perpendicular distance between the Z-axis, basically. And you can directly get that along the X-axis, right? Because I know my X is going to be perpendicular to both of them. So I can always look at the common perpendicular, which is along X1, to be able to get the like length A1. So A1 is the distance between, the common distance between the Z-axis. Alpha is the angle between Z0 and Z1 about X1. So by how much you actually, about X0. By how much you are going to be rotating Z0 to be able to arrive basically at Z1. And this basically has to be along the XI axis. D, so it's A, alpha, D, and then theta. D is the actual distance between the x-axis along the Z0 vector, right? So here you want to keep track of your vectors, right? So you have, so if I is 0, you have x0, x1 along Z0. So D is, you know, by what is the offset between x0 and x1 along the Z0 axis, okay? And then theta is the angle between x0 and x1 about Z0, right? Or if I is equal to 0, or I'm sorry, if I is equal to 1, right? Angle between x0 and x1 along what? Along Z0. So this is your theta. By how much you are basically rotating the vector x0 to be able to arrive to vector x1. Okay, I'm gonna have another lecture that is specifically for, you know, more in detail into the DH parameters. But, you know, today I just wanted to kind of give you an overview of the DH parameters. And what the DH parameters are is basically, ultimately we're going to write a DH transformation, and we're going to obtain the DH transformation based on these 4 values that you actually have. And usually when you buy a robot or industrial robot, they will actually give you those, so you will automatically have your DH transformations based on these variables, or you can basically get them from geometry. All right, so this is just an introduction to DH parameters. There will be another more detailed lectures on DH parameters with actual examples. After this lecture, I would like you guys to rework this problem yourself, and then also do it in Matlab, and make sure you fully understand how you actually do that. And regarding our assignments, basically, that I'm going to just post the assignments, but I will not collect the assignments. We will actually have the assignments. Basically, I'm going to grade you based on an exam, basically. So the exam will be kind of similar to the assignments, but it will obviously be different. So we're going to have 3 exams, right? Exam 1, exam 2, and then the final. So they will be 30, 30, and then 40. Okay, guys, so that is it for today.